exponential growth and decay. Exponential growth. This kind of thing happens everywhere. It happens with populations. I suppose I should say populations where there's plenty of resources and food and space and all that kind of stuff. Like if you put 3 bunny rabbits, well, let's put 12 bunny rabbits in a patch of woods, and the woods is big. The population's going to tend to go like this because they got plenty to eat, they got plenty of elbow room, hopefully there's not too many wolves. Anyway, populations tend to grow like this. Money in the bank, if you're getting compound interest, it tends to go like this. Of course, in reality, it takes us kind of a long time for our money to get anywhere to where it's increasing quickly. The old saying, it's the hard part's getting your first $1 million. But anyway, that's what compound interest will do. Exponential decay, that's when it goes something like this. Think of half-lives. Think of radioactive decay or some other things like that. So anyway, this stuff is everywhere. So let's take some of our college algebra tools and methods that we've been patiently building up for the past few weeks. Let's put them to use. First, on a population problem. The population of Dogpatch is growing. Yep. It was 124 in 1990, and there's plenty of space, plenty of food, and so on. So it was 217 when we got to the year 2015. So what's the population going to be in the year 2050? Well, I want to contrast exponential growth with standard linear straight line growth. Let's do this problem both ways. First, we'll use a straight line to estimate it, and then we'll use an exponential to estimate it. Okay, so a straight line, you'd do something like this. You'd say, let's put the year here, and let's put the population here. So it's kind of like our x and y, right? What year is it, and what's the population? So we were 124, that was our population, in 1990. And then we grew to, what are we now? 217 when we got to the year 2015. And then here's the question. What is it in the year 2050, right? There we go. Now, you could almost solve this just by trying to make a graph. Just say, well, here's 1990. And I'm at 124, so just try to plot that point. And then when it gets to the year 2015, which is, 25 years later or something, so just kind of come out here someplace. We were at 217, which I'm guessing is, I don't know, right around there someplace, right? And the question is, if we keep going as a straight line, and this is what we mean when we say linear growth, we say, just join those 2 points with a straight line and expect it to keep going that way. Where will it be in the year 2050? So where's that? That's like what is that? That's like 35 years later to get from here to here. So this was 25. Now we got to go 35. So it's a little bit different. So anyway, if you drew this graph to scale, you could eyeball the answer. I don't think I drew the graph accurately enough. But if you got out if you got out some real graph paper, preferably graph paper with really small squares on it, and you were very careful to plot your points, nice and accurately and all that stuff, you'd be able to read the answer and you'd come out pretty close. So that's one way you could solve it. Of course, what we might want to do is use an equation. That's the power of algebra. We can do things a little more precisely. So straight lines. Remember what straight lines are? Y equals mx plus b. That's called slope-intercept form of a straight line. Any straight line in the world can be cast into that sort of an equation. Y equals mx plus b. So, what's our slope and what's our intercept? Well, the slope we can get by doing that old rise over run thing, right? Let's just do that. Rise over run. And you can use any 2 points on your curve to figure out the slope. Might as well use these first 2 points, huh? So the rise here would be from, I was going to try to do it in my head, but I won't. So we went, the y2 minus y1 is a 217 minus 24, the x2 minus x1. Okay, that I will do in my head. I don't want to write down the years. I'll just say it was 25 years. Right? That is 25. Right, 25 years. So 217 minus 124 is, look at me losing my calculator. What a shame. Okay, 76, 86, 93? Yep, 93. Over 25. And I could make a decimal out of that, but I kind of don't want to. So the slope is 93/25. 93/25 is the slope. Now, what's the y-intercept? Here, I'm going to show you a cool trick. Oh, you're going to love this trick. Do you remember what we used to do to find the b? We'd have our equation, right? We'd have part of our equation because we know what the m is, but we don't know what the b is. So we'd be like, okay, what I got to do then to solve for b is I'll have to take one of my points that I know, plug in the x and y coordinates here and here, and solve for b. We don't have to do that. No, I got a heck of a trick for you. You're going to love this. What you do is you call this year 0. We start at year 0. Because if that's 0, remember, that's what the y-intercept is. It's what's the value of y when you plug in 0. So you just make that a 0 and go, boom, the y-intercept is 124. Woo-hoo-hoo. So if you call that year 0 at the start, you start in year 0, then the y-intercept is just whatever you started at. Boom, no calculations at all. And so we can finish our model this way. I'm going to be a good boy and write f of x instead of y, equals mx, 93/25 x, plus b, which is 124. But the thing is, x is the number of years starting in 1990, right? Starting in 1990. 1990 is year 0. So you have to count from 1990 in order to use that equation. But that's fine. That was great. I don't mind plugging in 0. So what was this? This was year 25, right? Because 25 years. And then what is this? This would be from 1990 to 2050. That would be year 60. So in order to answer our question, so I'm kind of going this way now. So plug in x equals 60 to get the population in the year 2050. And I'm just going to plug some buttons on my calculator real quick. So 93 multiplies, what now? 60. And then divides by 25. I'm going to hit equals. And then I'm going to say add that 124 to it. And I'm getting, if I round to the nearest whole person, I'm getting 347. So the population right there is 347. Looks reasonable, doesn't it? That's 124, 217, 347. I can believe it. Seems like it's in the right ballpark there. So anyway, that's how you could do a linear growth model. Just connect your, take the 2 points that they gave you. We started here. We grew this much in the first 25 years. Where are we going to be later? Well, just connect those two with a straight line and just kind of follow the line and see where you end up. Now, an exponential growth model might be a better model because, I always think of linear growth as a piggy bank model. I'm going to put a quarter in my piggy bank every day. So how much have I got in my piggy bank? Well, that grows as a straight line because it's add a quarter every day, add a quarter every day. Populations, especially bunny rabbits, but populations of people, again, when there's plenty of resources and all that, they don't tend to grow like straight lines. They don't really grow like that. They tend to grow like exponentials. So let's use an exponential growth model. So first I'll try to, let's start by making a graph. I guess I will need to make a table of year versus population, but first, what's the graph going to look like? It's going to look different. It's going to be, we will start at 124, and we will get to 2050. This is 1990. When we get to 2015, we will be at 217. Okay, right? This part's the same, right? Those are our 2 starting points. We have to go through those 2 points. So again, with a straight line, you would just get out your ruler and connect them. But if it's exponential growth, what you expect is there's like some kind of a doubling. It's like it keeps going up faster and faster. There's like a doubling period of who knows what. But it's going to keep going up faster and faster like this. It's going to follow one of those exponential curves. Just like graphing e to the x or whatever, it's going to follow this curve that starts to climb faster and faster. Now, what's the equation of that curve? Well, you don't use y equals mx plus b for this. What we use is, and you want to keep this handy, y equals AE to the KT. So this y equals mx plus b, you use that for straight lines. This is what you use for exponential growth. You want to keep this formula around. That's what you use for exponential growth. Now, the A is our starting amount. It's kind of like the y-intercept, right? But it's the starting amount at year 0. In other words, to use this model, we really do need to call that year 0. So that's year 0, and so A is going to be 124. 2015, again, that's year 25. Okay, so you have to, the A is the amount at year 0. It has to be at year 0 for this model to work. So we're going to have to call it 0, 0. Okay, we did. Good. Now the K, T, of course, is time going by. K is, well, it's a constant. What are you doing? Hey, man, it's a note. Do you see that? It's a note. Okay, anyway. K is called the rate of growth, although it's not really a slope. But it's kind of related in the sense that the bigger the K, the faster you climb. So they call it a rate of growth. Again, it's not going to be a simple slope. I mean, a simple slope is just up 1 over 1, up 1 over 1, or whatever. Right? That's not what this is going to do. It's going to curve. So K is something you have to solve for, basically. So let's come over here and start filling in our table. So I was going to say year 0. You have to start at year 0. We have 124 people. In year 25, in other words, 25 years later, our population was 217. And of course, we're trying to figure out in years 60, what is it? How are we going to get that K? Well, we're going to use this data point right here. When year equals 25, we're supposed to have y equals 217. So that means the y is going to be 217, is going to be A, which we already said is this 124, it's the starting amount, E to the K times T. Well, T is 25. So it's K times 25, which I'm going to write as 25 times K. We can solve that equation for K. First, divide both sides by the 124. Then, take the natural log of both sides. That cancels the E over here. Then, divide both sides by 25. So, K is equal to, take the natural log of this 217 over this 124, right? Divide it by the 25. That'll be your K, and let's see what we get. 217 is divided by 124. Hit my equals button. My natural log of answer equals, divide that by 25 equals, I've got 0.02238. 46. You do want to carry some decimals on this, because it turns out this equation is very sensitive to the value you put in for K. So you want to carry a lot of decimals on K to get it to work. But anyway, now that we've got our K, what that really means is that we can write our full equation. So again, A is the starting amount. We start at 124. E to the K, we just worked it out, 0.0223846 times the T. This is our equation. It's the equation of this curve. Now we can answer questions like, what if I plug in T equals 60? What do I get? So I'll let you, this is a button pushing exercise. It's worth getting out your calculator. Make sure you get the same thing as me. So I'm going to go like this. I'm going to go 0.0223846. I'm going to multiply that by 60, and I'm going to hit equals. Now I'm going to take E, which is a button on my calculator, and raise it to that power. Just use the answer key. Okay, and then I have to just multiply that by 124. And so I'm ending up with 475. If I round to the nearest person, it's 475. let's compare to what we had before. Compare to 347. Ooh, that's quite a difference, isn't it? If I were to do that on the same graph up here, 475, yeah, that's like way up here someplace, right? So this exponential growth, it really is doing something like that. Okay, so exponential growth, you're going to grow a lot faster than a straight line. That's the whole point. That's the whole point. Okay, so I guess the main thing to keep in mind is this formula. You got to keep that formula. We're going to use that for exponential growth. We're going to use the same formula for exponential decay. Okay. Speaking of exponential decay, let's look at the next one. The half-life of Bifanium-235. So we're talking exponential decay, like radioactive decay. It's got a half-life. This stuff has a half-life of 4,500 years. Okay. So we got a piece of rock, and this rock has 240 milligrams right now. So how much is going to be in the rock still after 10,000 years have gone by? Okay, so I was telling you, and I meant it, we're still going to use this kind of a formula. Exponential growth and decay follow this formula. Again, this is the starting amount. And by starting, we say at year 0. You have to start your counting at year 0. And then k is going to be some constant we have to solve for. And then t, of course, is time going by. So for this one, we're starting at, where is it? 240 milligrams. Cool. So we know that part of our formula already. The hard part is, how are we supposed to figure out what k is? Remember how we got k in the previous problem? We plugged in a data point, right? Well, where's my data point here? I need a data point of some sort. Well, here's a data point. You know that after 4,500 years, you should have only half left, because that's the half-life. The half-life is 4,500 years, means in 4,500 years, this should be down to 120. So there's our data point. We'll just kind of, make it up. If we did wait 4,500 years, that 240 would be half. It would be 120. So I'll just plug that in and solve it. 120 equals 240 times e to the, what am I plugging in? I'm plugging in 4,500 for t times k. There's our little equation that we can solve for k. You solve this one by, well, first divide both sides by 240. Equals e to the 4,500k. Then take the log of both sides. And by the way, 120 over 240 is just a half. And on the right side, the log cancels the e, so you get a 4,500k. So then you divide both sides by 4,500. And we end up with k equals, what have I got here? Take the natural log of 0.5. Boom. Divide it by the 4,500. Boom. K is, and it's coming out negative. You know why it's coming out negative? Because we're decaying, not growing. So you get a negative k when it's a decay. And it's a decay. So I get a negative, be careful, my calculator has scientific notation. It says times 10 to the minus 4. So you have to slide your decimal back 4 places. So this is actually point, let's see now here, 0.154.033. And like I say, you do want to carry some decimals, because these formulas, these exponential growth and decay things, they're very sensitive to the value of k, so you want to carry decimals on the value of k. Anyway, notice we've got the equation all finished now. So I've got y equals, remember the beginning amount was 240, and we just found that our k is equal to, and this is the hard part right here, is having to copy down your k. Negative 0.000154033 times t. There's our finished formula. That's a happy result. And now we can use that to make predictions. It wants to know how much will be left in 10,000 years. Plug in 10,000. By the way, just as a quick estimate, right? In 4,500 years, it got cut in half. Well, another 4,500 years, it'll get cut in half again. In other words, when we get to the 9,000 year mark, it should be cut in half again. So the 120 would be down to 60. We're going to go a little more than that, so it's going to be a little less than 60. That's what we expect, a little less than 60. Anyway, it's a button pushing exercise, so I invite you to push buttons. Make sure you can get exactly the same result as me. So I'm going to say, okay, negative 0.00154,033. Okay, multiply that by 10,000. Cool. By the way, I'm looking at something like negative 1.5. Anyway, e gets raised to that power. So e to the answer is, now I'm looking at like a 0.21. And then I multiply by 240, and I'm getting, remember I was expecting less than 60? I got a 51.4, and these are milligrams. Cool, right? So you can use these exponential growth formula for exponential decay, for half-life type stuff. It works just fine. Example 3, I wanted to do another half-life formula, or example. This one's just a little bit different because they're trying to ask you how old something is. But I would invite you to pause and give this a twirl yourself, just as a sort of a confidence check or whatever you want to call it. Pause. Come on back. Okay, where are we? We've got this half-life. Oh, it's the same stuff. Bethanium 235, half-life 4,500 years. Hey, you know what? That means I can take that K and use it. Yay, team. That's cool. Same thing, right? 4,500 years, right? Same thing. Awesome. We don't have to solve for the K. We've got the K already. So anyway, we're digging up an arrowhead now. So we dig up an arrowhead, and you assume that it used to have 240 when it was fashioned, but it now has 170. So how old is it? Okay. It was fashioned in year 0. And at that time, it was containing 240 milligrams. Wait a minute. Is that the same thing we had up here? It is. How do you like that? So anyway, whatever. So it was fashioned in year 0, containing 240 milligrams, which means our equation looks like this. 240 is the A, because that's what we started at. E to the, and it's the same K. We already figured that out, right? 1540332. It's actually the same equation as we had in the previous example. But now it has 170. Okay, new color. Now it has 170. The 170 goes here. And we have to solve for the time. So that's what's different. We have to solve for the t. We're not plugging in t, we're solving for t. Well, if we know how to solve for k, that's going to be the same steps here. First, divide both sides by the 240. So I have e by itself. Then take the natural log of both sides, and I might as well reduce that to 17 over 24. Just cancel 10s top and bottom. Like I say, the hardest part about these problems is copying the k's down. Then divide both sides by that negative 0.000154033. Right? Do that on both sides. And you've got t. T equals. Let's find out. So let's see here. Natural log. Do a 17 divide by 24 and close my parentheses. Divide by. Negative button. 0.000154033. Boom! 22. If I round to the nearest year, it's 2239 years. So it's 2,239 years later, which means the thing is 2,239 years old. That goes back a ways. Cool. And so that's how they do the carbon dating type stuff, right? Okay, cool. I'm going to end with something that's a little different. It's still a form of exponential growth and decay. You can kind of see the little e to a power down here doing something. But this is a somewhat funkier formula. And it's funkier because it's kind of like exponential growth with a twist. Exponential growth just goes like this. Hey, I'm starting here. Woohoo! You know, that's exponential growth. Well, that's not the way everything grows because, you know, this, again, this assumes, pardon me, this assumes you've got plenty of resources, plenty of food, plenty of space, everything's happy and hunky-dory, and you're just going, yay, team. Okay, that's not the way the world necessarily, it's not going to work that way forever is what I should say. Especially if you're like a flu virus or something, right? If you're a flu virus, you can't grow forever. You're going to run out of people sooner or later. What we typically have is something called the carrying capacity of our habitat. Let's call that maximum possible population. The carrying capacity, we call it the carrying capacity. So you might, if you just introduce a couple of flu germs or whatever into a population, at first it is going to kind of grow quickly. But then at some point, it's going to start to kind of sense, hey, we're running out of people, and it's going to get harder to find new, hosts or whatever. And it tends to level off like this towards the Pmax. So actually, the way this curve would look, if you graphed it in both directions, it would be kind of symmetrical like this. But the idea is you start here, it's kind of like hopping onto this curve and following it up towards our carrying capacity. This is called the logistic growth curve. So it's kind of like exponential growth that slows towards a limit. You grow exponentially at first, but then there's a limit. You can't grow forever, so you tend to slow down. And that slowing down is sort of an exponential decay of sorts, sort of an upside down exponential decay. It gradually approaches the carrying capacity. So anyway, that's what we're talking about when we talk about logistic growth models. So we've got some parameters here. First of all, P of t, that's the population as a function of time, right? P max, that's the carrying capacity I was talking about. P naught, that's your starting population. So whatever this value is here, that's called our P0, P naught. That's our population at time 0. Because this, again, we have to call that time 0 for this formula to work. That's time 0, that's time going by this way. Okay. Now, B is the, quote, natural constant, called the rate of growth. Just like in the previous example, like this one up here, we had to solve for the K, right? We had to solve for our K. We needed a data point to do that. For this one, we're going to have to solve for the B. So you'll need a data point to solve for the B. But once you've solved for the B, you've got the full equation and you can use it to make predictions. So, cool. Hope you're digging this. Now let's try using it. Okay, example 4. Oh, it is a flu virus. Look at that. Okay, so we got a flu virus. Introduced it to 100 people on day 0. Okay, so I don't know if I want to do this, but I will. I'm going to say day and I guess population, right? Or I guess it's the number of infected people is what you would say, right? So anyway, on day 0, we had 100 people infected. 80 days later, okay, on day 80, we had, 10,000 people? Okay, that's a little bit more. So I completely made these numbers up, of course. I hope you know that. This is all just, it's for fun. So anyway, we have 10,000 people later, 10,000 people on day 80. Okay, cool. Now, we're going to assume a carrying capacity of 8 billion. That's saying that the Pmax is 8 billion, which is roughly the world population. Why not? Just do the whole world. And how long will it take for half the world to be infected? So that's the question. How long will it take? What day will it be when half the world is infected? Well, if the whole world is 8 billion, then we're wondering how long is it going to take for 4 billion to be infected, right? So that's kind of our XY table summary of what we're trying to do here. So we know the Pmax is 8 billion. They told us that. We want to use this formula. This formula has an A in it, and the A is defined this way. Let's figure out what the A is first. So you take your Pmax, which is 8 billion. Boy, this is Should have used smaller numbers. Oh well, 8 billion. And you subtract your P naught, which was 100. And then you divide it by your P naught, which was 100. And so A is going to be something crazy. Let's see what we got here. 8. 1, 2, 3. 1, 2, 3. 1, 2, 3. That's 8 billion. Subtract 100. Ooh, okay, that means there's 7. Oh boy. And then divide that by 100. Ooh, here's our A. 7 with 7 nines after it. 1, 2, 3, 4, 5, 6, 7. Let me make sure I counted that right. 1, 2, 3, 4. Okay, a 7 with 7 nines after it. Huh. So if I put commas, it's going to be like this. So A is a 79,999,999. Okay, that's interesting. Now we can write most of our formula. P of T is going to be, put the P max on top, put the 8 billion on top. Boy, I wish I had used smaller numbers, but that's okay. I got a calculator, it'll work. 1 plus, and it says A times, so now that's where I put my A right here, 79,999,999, e to the, and it says negative BT. Now that negative is part of the formula, so always put that negative there. That negative is part of the formula. Here is our half-built formula. Just by figuring out that A and the carrying capacity, we were able to just, boom, we've got half the formula. What's missing, of course, what's missing is we don't know what B is. And that's where you have to go get another point. So I'm going to switch back to blue here. This point. When T is equal to 80, the population is supposed to be 10,000. So we're going to plug that information in and solve for our B. Okay, we might need more than just this sheet of paper to do it, but let's do it. So P of T is going to be 10,000 when 1 plus okay, when T is equal to 80. So I got a negative B times T is going to look like a negative 80, and that's a B. Cool. You want to solve that equation for B? What should we do? What should we do? How should I explain this? I have something I want to do, but let's do this. Let's make it look like a proportion. So now I can say the cross products are equal, right? I'm not crossing it off. I'm saying the cross products are equal. So on this diagonal, I've got 10,000 multiplying all of this stuff. 1 plus all that. And on the other diagonal, 1 times 8 billion is 8 billion. Okay, first thing I'm going to do to try to get B by itself is I'll get the parentheses by itself. In other words, I'll divide both sides by 10,000. So now I've got 1 plus 79, 999, 999, e to the negative 80b is equal to. Now if you take 8 billion and you divide it by 10,000, what are you going to get? Well, I'm going to cancel off 4 zeros. 1, 2, 3, 4. And that's really all I got to do is cancel off 4 zeros. So I've got 8 with 1, 2, 3, 4, 5 zeros left. So that's an 800,000. Okay, subtract 1 on both sides. What do you say? Subtracting 1 from 800,000, you get 799,999. These are such fun numbers. Oh, look at this now. So now, in order to get the E part by itself, that's an 80, by the way, not an 8. 80B. 80B. Come on, come on. 80B. Okay, in order to get the E by itself, I'm going to have to divide both sides by 79,900,000. And I'm not going to turn that into a decimal because, like I say, these things are highly sensitive to the number of decimal places you carry, right? Warning. Highly sensitive to a number of decimal places. And that's why I am not going to turn this into a decimal. I'm going to let my calculator worry about it later. Anyway, I got the E there. Take the log of both sides. Remember how this stuff works? Natural log of, and if you don't mind, I'll just say that goes in there. And then the last thing you would do is you would divide both sides by negative 80. So the natural log of, yep, that stuff goes there, is being divided by a negative 80. Woody, hooty, hooski. Okay, now I'm going to have to get a decimal. So, 799,999, that's going to be divided by 79,999,999 equals. And now I have to take the log of the answer, equals. And now I have to divide by a negative 80 equals. I've got B equals, boy, it looks like a normal number compared to what we've been playing with. 0.0575. I want 6 sig figs. 575,646. I'm carrying 6 what we call significant digits. The 0 in front never counts. So 575,646. That's 6 figures of accuracy. That's to the nearest millionth. That's pretty close. Okay. What's that mean? That means we can finish our equation now, because now we know, because now we know what the B equals. The B equals this. So our finished equation, let's go back to like green. So our finished equation, is, I'm basically going to take, I wonder if I could just do a copy paste. That'd be cool. Copy, not cut, copy. Come on down here. Paste. Oh, beauty. That's the first time I ever did that. I'm stoked. Okay, so anyway, we figured out, come on, eraser, you can do it. Oh, I get it. It posted it as an image. Oh. That's okay. I'll cope. So we're going to have P of T. In fact, I'll use a different color now. Now I'll use like purple. So P of T is equal to 8 billion over 1 plus 79,999,999 times e to the negative, and I put my b in there. Woo! 0.0575646 t. There is our finished model. That is our logistic growth curve. That's the equation of our logistic growth curve for this particular whatever kind of germ it is. What was the question? The question was, okay, how long will it take for 4 billion people to be infected? Okay, so set P of T equals 4 billion, solve for T. That is our task. Okay. Wow. Okay, well, here we go then. 4 billion equals 8 billion over 1 plus 79,999,999 e to the negative 0.0575646 t. Can do the old cross product thing again. 4 billion times 1 plus 79,999,999 e to the negative 0.0575646 t equals 1 times 8 billion. Now if I divide both sides of my equation by 4 billion, I'll have this bubble here, 1 plus 79,999,999 e to the negative 0.0575646 t is equal to 2. 8 billion divided by 4 billion is 2. Now I subtract 1 on both sides. 2 minus 1 is 1. Okay, divide both sides by that big number. So e to the negative 0.0575646t is equal to 1 over 79,999,999. Take the log of both sides. That'll cancel the e. So I've got a negative 0.0575646t is equal to the natural log of that. And then divide both sides by that decimal. We're almost here, folks. So take the natural log of that same thing, but divide it by negative 0.0575646, and you'll have your time. How long will it take for the population, half the world's population, to have this germ? Oh, I can hardly wait to find the answer. So I'm just looking back up here because I'm curious now. It took how long for what now? It took 80 days to reach 10,000. 80 days for 10,000. How long is it going to take to reach 4 billion? Let's find out. So I got to take the net. Okay, first of all, I got 1 divided by 79,999,999 equals. I take the log of that teeny weeny number equals. I divide it by the negative 0.0575646. And I get, oh, you're hardly going to believe this, 316 days. Wow. Now, I did just completely make those numbers up, so I don't know. But in case of that kind of a germ situation, it's like, oh, wow, half the world in less than a year? Yeah, maybe you know, maybe you want to shut some things down. I don't know what's going on. I just made it up. So anyway, that's an example of the logistic growth curve. So the numbers were big, but hopefully you could focus on the procedure there. You know, the procedure being first figure out what your A is so that you can write most of your equation. And then solving for B is going to be, well, the hardest part is that you have to schlep along all these big numbers for this one. But I think in the homework the numbers aren't going to be quite that big. But I did want to do one of these flu examples. Cool. 316 days. Cool. All right.